So in the past 2 weeks, we've been looking at applications of functional analysis in Hilbert spaces. What have we seen? Well, we've seen that we can solve linear equations, and we've seen that we can diagonalize self-adjoint operators. So a lot of the power of linear algebra can be extended from finite dimension to infinite dimension, as long as the infinite dimensional space you're working with is isomorphic to a Hilbert space. And this is very nice consequences. We just got a glimpse at it in applications to partial differential equations. I mean, linear algebra really revolutionized in the 19th century, mostly, the solution of ordinary differential equations and questions of optimizations in calculus. And with the advent of functional analysis in the early 20th century, what you've seen is that working in Hilbert spaces, that power of linear algebra was extended to infinite dimension, and you could move from solving ordinary differential equation to solving partial differential equation. You can move from optimizing functions of a handful of variables to optimizing functions themselves, so optimizing over vectors in your Hilbert space. So this is extremely powerful. We've just scratched the surface of the applications. I didn't really talk about the algebraic applications to representation theory. You can look at algebraic object inside the space of bounded linear operators acting in a Hilbert space, and this brings a lot of techniques from linear algebra into algebraic context where you wouldn't see linearity to start with. So this is extremely powerful, but this is one limitation, and the limitation is that we're working in Hilbert spaces. Maybe we might also want to do the same sort of thing in other infinite dimensional vector spaces. Banach spaces. Typically that may not be isomorphic to a Hilbert space. Think, for instance, of the space of integrable function, resonance square integrable function. Think of spaces of continuous functions. They will be good examples of spaces in which you might want to carry the same sort of analysis. So to a large extent, the rest of the course is going to be all about extending what we've seen in these first 2 weeks, all the powerful linear algebra that we can do in Hilbert spaces to more general Banach spaces. We want to know what sort of Banach spaces would allow us to do that and what the generalization would look like. Now, you should be asking yourself two questions. You should be asking yourself, why and how are we going to do this? So the question why is important. I mean, maybe let's just use Hilbert spaces as an infinite dimensional generalization of Rn, and that would be good enough for all practical purposes. It's true that Hilbert spaces are used in really a lot of applications, and not that many people maybe need non-Hilbertian Banach spaces in there to do their infinite dimensional analysis. But okay, let me give you some possible motivation. One, we got a glimpse at when I told you about regularity theory of partial differential equations, right? What did we see? We saw that if I have an element of L2 which has one derivative in L2, so it's in the sub-L space H1, then such an object will have a continuous representative. And that's one way, when you look at ordinary differential equations, to move back from just having a weak solution, which is good from the point of view of an existence theory, to having a classical solution. That gives you a lot more information and a notion of solution that maybe is a lot more satisfying. Now, I did it in one dimension on purpose. It's simpler there, and having one derivative in L2 was enough to guarantee the existence of a continuous representative. If we were to work in higher dimension, then what we would see is that either we need more derivatives in L2 to get the sub-F embedding, or we need one derivative in LP for a sufficiently large value of P, and as soon as P is not 2, then LP is not going to be a Hilbert space, just a Banach space. So if you're interested in regularity theory of partial differential equation, you're bound to have to deal with at least LP spaces for P not equal to 2. That's one motivation. If you're interested in PD, there are many more motivations. So in particular, there's motivations coming from scaling of equations. So equations have certain invariances, and you might want the norm of the space you're working on to respect those invariances. These invariances usually have a physical meaning. So if you have a norm that doesn't respect the physical invariance of the problem, it probably doesn't make a lot of physical sense. But even if you don't care about that, from a pure mathematical point of view, that's kind of a general principle here. If you have invariances in your problem and you use tools to solve your problem that do not pay attention to those invariances, you're very unlikely to get optimal solutions. So in PDEs, sometimes the scaling of the equation is nice enough for us to work in L2. Sometimes it isn't. Case in point, the very famous Navier-Stokes equation, the basic equation of fluid mechanics, the appropriate LP space in which to work on that will respect the scaling of the equation is the space LP where P is equal to the dimension. So you can work in L2 fine if you're interested in two-dimensional fluids, but if you're working in three-dimension, for instance, you have to work in L3, and that is not a Hilbert space. And we can go on and on. I like probability, and probability, if you only work in Hilbert spaces, that means you're only discussing variances of the variables you're interested in. You might be interested in their mean, and then working L1, you might be interested in other moments than just the second moments of your variable. So these are the reasons why we're going to need to move beyond Hilbert spaces. Now, some of the reasons why, there are many more. Geometric group theory, for instance, is interested into embedding groups in certain Banach spaces, and L2 is very relevant, but that is not the only relevant space. Now, the bad news is that it's hard. Hilbert spaces are really beautiful Banach spaces. They have all sorts of extremely helpful properties. This is the Riesz representation theorem, so you can identify the dual with the space itself. Every subspace, closed subspace is isomorphic to the space itself, or isomorphic or finite dimensional. These kind of properties make life really easy, and that's why with the theory you had learned in analysis 2, you were already able to go to very powerful application, right off the bat in the first 2 weeks of this course. Now, to do things in Banach spaces, we're going to need to build a fair bit of machinery, topological and analytical machinery, in order to mimic these good properties of Hilbert spaces in other Banach spaces. Now, let's stop for a second, look back at those theorems that we're trying to generalize and think about what we need. So the Riesz representation theorem was all over the place, and bad news, it's not going to be available in general Banach spaces, not at all. So what we're going to need to use instead is, instead of just having the space and sometimes identifying it with its dual, as we do in the Riesz representation theorem, we're going to have at least a pair, the space and its dual space. So duality will be a key theme throughout the rest of the course. So we're going to start with that, just understanding what dual of Banach spaces look like and what we can do with them in the first part of this second part of the course. Now, that's a key thing, duality. We actually both wanted to solve minimization problem and use solution of minimization problem in the building of our theory. So the ability of projecting onto a convex subset was particularly relevant. So convexity played a role. Now in Hilbert spaces, the unit ball looks really like a ball in standard unit ball in finite dimension. It's very nicely convex, and that helps with minimization question. So the level of convexity of the unit ball of your Banach space will play a big role in how much of an extension of results from Hilbert space theory you can hope to achieve. So convexity will be also a main concept in what we do next. Okay, but let's get started and let's have a look at this duality of Banach spaces and its basic properties to start with. So first things first, basic definitions and notation. If I have two Banach spaces, I'm going to denote by B of xy, the space of linear and continuous maps from x to y, B standing for bounded. So I keep reminding myself that continuity and boundedness is the same for linear maps between Banach spaces. When I look at B of xx, so maps that from x to itself, I'm just going to denote it by B of x. And when I look at the dual space, so the linear continuous map from x down to the underlying field of real number, I'm going to denote it by x star, just like we did also in Hilbert space theory, except this time x star will not be identifiable with x, not generally speaking, definitely. Now, I don't have a inner product in a general Banach space, but I have a duality product, which is a bilinear pairing between the space itself and its dual. So because it's going to work in a way that's very similar to the inner product in a Hilbert space, I'm going to use the same notation to remember that it generalizes this inner product into a duality product between x star and x. So I'm going to have the duality between x and x star, or the duality between x and x star, being defined as the action of the linear functional x star onto x, right? So this is going to be a notation for this number that is x star applied to x, and I'll use the same notation with the role of x and x star reversed. Okay, so these are the basic notation we'll be using. The first thing we want to show really is that x star is itself a Banach space. So you should ask for which norm? Well, for the norm that you get from seeing it as a space of bounded linear maps. So the supremum of the action of x star onto x when x is in the unit sphere, right? So it's a norm on a space of continuous functions, so continuous on the unit sphere of your Banach space x. Now, I'm going to have to show that this is a norm and that this makes x star complete. That's going to be theorem 4.3. So the first thing I need to make sure of is that the supremum at the very least is finite, right? Such that this norm on the dual space is well defined. And that's very simple. So I might just do it here. So how do we prove the lemma? Okay, well, you just use the definition of continuity. So by continuity, we have that there exists a delta such that for all x in x, x star applied to x minus x star applied to the 0 vector is smaller than 1 whenever x is smaller than delta. All right. Okay, so what does that tell me? That tells me that for all x in x, whenever x has norm smaller than 1, then the action of x star on delta x, delta x will have norm smaller than delta, is smaller than 1. And therefore, whenever x has norm smaller than 1, when particular norm equal to 1, then x star x is smaller than 1 upon delta, and that certainly is some finite number. So that's just the proof of lemma 4.2, and now we get to the real bit of work that we need to do, which is show that for this norm x star is a Banach space. So show that this is indeed a norm and that x star is complete for this norm. Let's do that now. Okay, so let's say that x star, the dual of x, is a Banach space for the norm that we've just defined. So let's start with triangle inequality for that norm. Let's take two vectors and the dual, and let's have a look at the norm of x star plus y star. What is it? Well, by definition, it's the supremum of x star plus y star applied to x for x of norm 1. But that's a supremum of a sum that's certainly smaller than the sum of the suprema. And the sum of the suprema is literally the sum of the norms of x star plus y star, the way we've defined them. So we have triangle inequality. Now, if we give ourselves a lambda that is a real number, maybe not 0, and we look at the norm of a lambda x star, then this is the supremum of lambda x star of x for any x of norm 1. If lambda happens to be positive, then you're multiplying the supremum by a positive number. If lambda happens to be negative, then you can look at the supremum applied with minus x instead of x, and then replace lambda by minus lambda. Now, in all of these cases, the supremum, because you can always replace x by minus x, is going to be the same whether you multiply by lambda or absolute value of lambda. And because when you multiply a supremum by a number, you just multiply it by this number. So this is lambda times the sup, which is mod lambda times x star, and that gives us the homogeneity of the norm. And is it really a norm? Well, if x star is as norm equal to 0, that means that for every x in x, if x is norm 1, then x star of x is 0. But by linearity, that really means that for every x in x, x star of x divided by its norm is 0, and that is literally saying that x star is 0, right? It's a linear map which sends every vector to 0. So what we've defined here is indeed a norm. Fine. Now the one thing that's really to prove is that the space capital X star is complete for this norm. So okay, let's take a Cauchy sequence. And try to construct a limit for that Cauchy sequence. So what have we got? When we look at the action on some x, let's say that has norm 1, then we have that xn star x minus xm star x, let's take some n and some m in n, is going to be, well, it's xn star minus xm star applied to x. So this is certainly smaller than the supremum, and therefore it's smaller than this norm. So if xn is Cauchy for the norm of x star, then we have that xn comma x is Cauchy for all x of norm 1. But even if you were to remove the norm 1 assumption and just make that smaller than 0, then, well, any x that is non-zero, you could divide by the norm of x, and then this result would still be true. So you could still get that xn star x is Cauchy for all x in x. Of course, for 0, it's obvious because it's constantly equal to 0. So it's Cauchy. It's Cauchy in where? It's Cauchy in the space of real numbers. So we have a limit by completeness of R, and Lx equal the limit as n goes to infinity of xn star applied to x exist for all x. Now, I want to show that this L is actually defining an element of x star, right? Well, it certainly is linear. L is linear because xn star is, and well, and that's it. And so all I really need to show is that it's continuous. That's going to tell me that it's an element of x star. And then we're going to show that xn star minus L in x star tends to 0 as n goes to infinity. So that's, it is indeed the limit. So let's show continuity first. It's a linear map, so to show continuity, I really only have to show boundedness. So the first thing I'm going to do is I'm just going to pick n large enough such that ln of x, so fix an x, and then I pick an n which is going to depend on that x, fair enough, such that L of x minus xn star x is smaller than 1. Can do that because it goes to 0 anyway. And then I have that L of x in absolute value is smaller than 1 plus absolute value of xn star x, and xn star is smaller than its norm. Let's assume that my x is norm 1. Okay, so I have that L of x is, well, norm smaller than 1. and I'll just take norm 1. If I can show, of course, by linearity, if I can show that L of x is bounded for all x of norm 1, then I get that L is continuous. So I have this, and this is certainly smaller than 1 plus the supremum over n of the xn star, which is finite because xn star is a Cauchy sequence. So if you're Cauchy, you have to be finite. Okay, so L is itself an element of x star, and I have to show that this is the limit of my xn star. So how do I do that? I use the fact that it's Cauchy, so I'm gonna let n in n be such that norm of xn star minus x capital N star is smaller than epsilon. Let's give ourselves an epsilon for all n greater than n. Sure. And then given an x, in x, let's say of norm 1, because that's enough to look at those, I'm going to let nx be a natural number that depend on x, be such that, okay, such that L of x minus x n star of x is smaller than epsilon for all n greater or equal than n of x, and I'm going to choose that n of x greater than n, right? I can always pick it further if it happened to be smaller than capital N. Right, so L of x minus x n of x is smaller than epsilon, and the norm of xn star minus x capital N star is smaller than epsilon, and that's all I need, because now what can I say? I can say that the norm of L of x minus the norm of xn star of x, what do I want to say? Let's call it xj star, is always going to be smaller than L of x minus x capital N of x star of x plus x capital N x star of x minus xj star of x. So for all j greater than this capital N, which is independent of x, and for all x in x that has norm 1, L of x minus xj star of x is smaller than this quantity. The first quantity is smaller than epsilon, and the second quantity is smaller than the norm of x nx star minus xj star, which, because n of x has been chosen greater than capital N, and j is also greater than capital N, then this is smaller than 2 epsilon, right? And this is independent of the choice of x. So for every epsilon, there exists an n such that for all j greater than this n, norm of L minus norm of xj star in x star is smaller than 2 epsilon, and so L is the limit of the xj star. And that concludes the proof that capital X star, the dual of a Banach space endowed with its natural norm, looking at the continuous linear function always the sup norm of continuous function, is itself a Banach space. Now the pair xx star and the duality pairing that we have between the two is going to be used throughout this course. This is going to be the replacement, the tools that we need to use as replacement of the Riesz representation theorem.